All right. Can you see the screen?
Yes.
You can see the screen. Yeah, okay, good. And you can hear my voice, right?
Yes.
Okay, good. So last time we were looking at, like I was saying, we started looking at how to incorporate electroweak symmetry breaking in the MSSM. The key point again is that before that we said, okay, when you write the most general SU2 cross U1 Lagrangian or the superpotential, there are terms in the superpotential which violate virion and lepton number. And so we impose something called R parity, which leads to conservation of removing of these terms and conservation of the proton. It keeps the proton stable. Furthermore, it gives something extra. What does it give you extra? It gives you that the lightest supersymmetric particle cannot decay. Okay, the lightest supersymmetric particle cannot decay. In the modern language, it's also called lightest observable sector particle sometimes. Okay, we'll talk about it later on when we come to supersymmetric breaking to distinguish these two. The lightest supersymmetric partner cannot decay. And we saw that all this is true at the renormable level. Non-renormable operators can break R parity violation. Now, once R parity is conserved, we'll consider what are the possibilities of having electroweak symmetry breaking. So we say that the Higgs gets vacuum expectation value. Okay. So we talked about a little bit about the hidden sectors and so on. So all the soft terms. The Higgs potential, we wrote down the Higgs potential. Always remember the scalar potential of the supersymmetric partner, supersymmetric theories is nothing but F square plus D square. So this is what we have written it all through. F square plus D square is the scalar potential. So that is the reason if F gets a vacuum expectation value or D gets a vacuum expectation value, you can break supersymmetry. But actually, what is F? F is a combination of some visible sector fields. Actually, each F is a combination of some visible sector fields, as we have seen. So, for example, in this case, the F terms are just nothing but mu square H2 square, mu square H1 square, essentially. Okay. Now you want to set these one of the H1s or H2s to get a vacuum expectation value. Just like in the scalar components of the H's to get a vacuum expectation value. The F term is still zero. Essentially, you're not breaking supersymmetry here. You're not breaking supersymmetry here. Okay, you're really breaking what do you call the vacuum expectation of the F is 0, whereas you're still breaking you're breaking electroweak symmetry breaking. Okay, but anyway, because F term will be proportional to the soft supersymmetry breaking terms, because you'll get these soft supersymmetry breaking terms here. Okay, we are having which are already supersymmetry is broken, explicitly broken. So we already have this soft supersymmetry breaking terms. And so you write down, this is the Higgs scalar potential. And now when you minimize this, assuming that both the Higgses get a vacuum expectation value, you end up having these two formula, which are the most important formula for any supersymmetric MSSM formula, which are called the minimization conditions. Okay, before, how did we derive that? We derived that assuming that the potential is bounded from below, which gives you these conditions, and also these two conditions. The determinant should be negative. So that means that one of the Higgses, MH2 or at least MH1 square, should become negative. Now, there are a few subtle points in this bunch of equations. This is your minimization conditions, which we covered last time. These are the two conditions. Now, MH2 square can become negative. So the total, this entire term becomes positive. MH2 square typically becomes negative because it couples to the top quark. And so runs through radiative corrections, MH2 square becomes negative. MH1 square can remain positive, so that the total MZ square should always be positive. MZ square should always be positive. Okay. This formula also requires you that mu square should be real, essentially, because mu square cannot be imaginary. We don't want imaginary components for this because mu should be real. So mu square should be real. Okay. And also, now if mu square becomes negative, also is a problem actually. Okay. Mu square should not become negative. Okay. Mu square should remain positive. If mu square becomes negative and if it becomes larger than this entire thing, okay, so in the limit MH, this adds a positive contribution essentially. Okay, so these conditions are important that, for example, you can see it better here essentially. So mu square should always be positive, so that the minimization conditions are always be satisfied essentially. This is one more mu square. Okay, I'll just show you one more formula. Okay, anyway, okay. Now so MH2 square can become negative. So the total, this entire term becomes positive. And tan beta is always positive. V2 by V1 is always positive. So MZ square should always be positive. The main thing, the condition is that MZ square should always be positive. And it cannot be, MZ square cannot be negative because we don't want any imaginary components into it. But of course, this is all true at the tree level. All these minimization conditions are only true at the tree level, but let's say that this is true. And secondly, if B mu can be decomposed as B mu times mu. Okay, B mu on this term here, 2 B mu, I wrote it down. B mu can be decomposed as B mu times mu. Okay, so here also you would assume, because sin 2 beta should be positive, so you want B mu should not be negative actually. Mu should not be negative. Mu can be negative, but what I'm going to say is, I'm sorry, I shouldn't say this. Sin 2 beta can be negative also. It cannot be imaginary. You don't want it to be imaginary. You don't want an imaginary component. But there could be a phase on the mu. There could be a phase on the mu. I'm saying as long as, okay, let me put it this way. As long as you are not considering CP violation, let's just say that let's keep this to be real. Okay, let's keep this to be real. Okay, in all these relations, actually, I should be more careful. The ones which comes is mod mu square. So the mod mu square should not be negative. What I mean to say is the radial component of mu square should not be negative, in the sense that it should always be positive. That's the condition. The radial component of the mu should always be positive, because the radial component of any complex number should always be positive. That's all it means. So I think when I said mu square, you remember that in these minimization conditions, it is always the modulus of the mu square which comes into the equation, essentially modulus of the mu square. Okay, otherwise, I'm sorry if I'm confusing you. I confused you. Okay, now maybe this makes life easier. So the moment I put in a modulus, now you can easily say that this cannot be, the modulus cannot be negative. So it should always be positive. So this gives you an important condition. Now you can have this to be negative. Like I said, this to be negative. So the entire thing becomes positive. And this also can turn negative because you need a wave for the second Higgs also. Suppose V2 and V1, both of them attain waves. M2 square will become negative. MH1 square also becomes negative. but the total sum will typically be positive. Will typically be positive. Remember, tan square beta is always tan beta is always greater than 1. So this denominator will always be positive. This denominator will always be positive. So this entire term would become a positive term. The modulus of the mu square is always a positive term. So you should get mz square here essentially. Now the entire, whenever you are dealing with supersymmetric spectrum, the entire problem comes because you are matching supersymmetric breaking terms with standard model terms. Now, the entire electroweak symmetry breaking incorporation in the standard model ends up giving you these connections between supersymmetry breaking and standard model parameters, and that is the main source of conflict of MSSM. So you cannot just say that, okay, I take all my supersymmetry breaking terms very high. Let me push it, the spectrum to be very, very high. You can push it, but it leads to these conditions to be satisfied at a very high precision. So suppose imagine these terms are MH2 square, MH1 square are very, very large. So they're sitting at, I don't know, gut scale or something. But the cancellations should be in such a way, the cancellation between these terms should be in such a way that you generate mz square out of this. Okay, this entire thing is the source of fine-tuning or conflict in the MSSM. Okay, so you cannot push arbitrarily very, very high soft term. So the moment you incorporate electroweak symmetry breaking into MSSM, you have relations between the soft supersymmetry breaking terms, which are controlling the supersymmetry breaking sector. How much is the masses of these soft partners, supersymmetry partners, and then the standard model partners, the standard model parameters like mz square, okay, and SUSY conserving parameters like mu square and so on. So this conflict is a major conflict actually. This is the reason why you end up all this talk about fine tuning and so on. So will appear here. Okay, this is the source of the conflict that you're trying to. You cannot just arbitrarily set supersymmetry soft terms, all of them to be very, very high, and so you can forget about there is a price to pay. Okay, you can forget about you'll generate standard model anyway. So you can all the soft terms you push them heavy. So supersymmetry has nice field theory properties. They should decouple very fast. So you should set them down. But then the price is, if you want to get MSSM, I mean the standard model parameters out of them, the price to pay is that they have to be fine-tuned very well. They have to be fine-tuned so that you get your standard model correctly, essentially. This conflict happens in every sector of the spectrum. This conflict happens at every spectrum, wherever there is a contribution coming from the electroweak sector, essentially electroweak symmetry breaking. So if you have some contribution proportional to the Z mass or W mass or so on, so you'll see that you cannot just set all the SUSY parameters very, very high, and then you can set it, but if you want to have something comparable, so there is always this if you want, you cannot change if you want. Okay, I'll tell you more about it in a second. When I look into the spectrum in every sector. Okay. Any questions about this part about the minimization conditions? Because this is important that we will talk about this about when we come to fine tuning. So these are tree level, but even if you have radiative corrections, the features roughly should remain the same. Essentially, what I was saying, that the connection between soft terms and SUSY breaking terms and SUSY conserving ones and the standard model parameters is the source of the conflict actually. Okay. Any questions here? Okay, good. Okay, so now today we will see the other sectors where we can have where we will study the supersymmetric spectrum. How does it appear? Essentially, the first one. Let's look at the most interesting one. Okay, we can look at everything, but let's just start with the first one, which is interesting for the dark matter sector, which is the neutralino sector. This is the easiest. The neutralino sector consists of collecting all the neutral fermions of the theory. These are SUSY ones only, okay, SUSY partners. They mix when Higgs gets vacuum excitation. When the Higgs fields gets vacuum excitation value, okay, the neutral components which are there, they start they get vacuum. They start mixing. Okay, so what are the neutral components in MSSM? So these are the neutral components of the agenose, which is essentially BNO and VNO. So I'll put a 0 here so that to distinguish between a neutral component and a charge component of the W, essentially. Okay, so there is a VNO and a VNO, which is this mix. This should mix to form a 14O and this one. And then, but then they also mix with the Higgsino. Okay, these four start mixing with amongst themselves. Why do they mix? Remember that scalar potential has Yukawa-like terms from the gauge interactions. Okay, so you have terms when starting from H dagger e power GV H. Okay, you can write it for 1 and also H2 dagger e power GV for H2, and then theta bar components. Remember this, we have seen it in QD, we have seen it in MSSM and so on. So this leads to components which are like Higgs, scalar, and then you have the gaugino, so it should be the VNO, and the Higgsino, so psi of H10. So there will be terms which are Yukawa-like times the gauge coupling. Say, for example, in this case, it will be G. Similarly, you'll also have terms like G1, Higgs, for both the Higgses, 1, 2. So both the Higgses, 1, 2. So BNO, okay, psi H10, H20. So once the Higgs get a vacuum expectation, so you have G1 sitting here, and when the Higgs gets a vacuum expectation value, it gives you a mass term for this mixing term. So that's how these mixing terms come. And whether it is V1 or V2, so whether it's V1, it gives you, whether if it's V2, it gives you sine beta. If it's V1, it gives you cos beta. So on. So you can write a neutrino mass matrix L, which contains psi n pa mn psi n plus hc. Actually, it's a Marana type mass matrix. Okay, you can write it as cyan transpose cyan. So Mn. Okay, you can further. Let's write in this particular format. Okay. So let's start it this way. Okay. So with cyan in the basis, you can choose P, Vino. I didn't put a 3, I think. Okay, let's remove this 3. Vino, Hexeno, Hexeno 2. In this basis, Mn is given. This is the famous neutral mass matrix. M1, 0, minus Mz, cos beta, sin theta W, Mz, sin beta, sin theta W, zero M2, Mz, cos beta, cos theta W, Mz, sin beta, cos theta W. Now this matrix is symmetric, so it should be the same thing, and then 0 minus mu, 0. So why it's symmetric? It's complex symmetric. It's because it's a Marana mass matrix. Okay, so Marana mass matrix. So the Marana mass matrix are complex symmetric. So that means what it means is that their M transpose is equal to M. This is the only thing. M dagger is not equivalent to M. It's not Hermitian. Okay, it is M transpose is equal to M, but M dagger is not equal to M unless you choose. Okay, unless you choose all the entries to be real. Now, let's go through this mass matrix a bit more carefully. Okay. Now, these are your soft terms, which are your Hexeno, Vino mass term, and the Vino mass term. And this is your mu term, which gives you the Hexeno mass term. Okay, which always connects H1 to H2, so H2 to H2, H1 to H2. So it gives you the off diagonal entry here. And diagonally, there is no Hexeno mass term, which is diagonal. And then, because it's not gauge invariant, because this comes from superpotential, this comes from superpotential, this comes from soft Lagrangian, this comes from soft Lagrangian. And after electroweak symmetry is broken, you have these terms. Okay, you have these terms. I think there's a sign here. You have these terms after electroweak symmetry is broken, which are generated, which are proportional to Mz. Okay, now, so if you see this at this level, okay, so you can, suppose if I say all the SUSY parameters are very, very heavy, all the SUSY parameters are very heavy. Say, let's just take M1, M2, mu, much, much heavier than Mz. Then you see, you'll have a pure Vino, and pure Hexeno. Now, which of them will be the lightest depends upon the parameters between these three parameters. Which is the smallest will determine which is the lightest. Okay. If it is Bino, M1 is very small, then it will be a pure Bino, the LSP. M2 is very small, then it will be a pure Vino. If mu is the smallest entry, it will be a pure Hexeno state, essentially the lightest particle. But essentially, all the neutrinos will just become Vino, or Hexeno states, essentially. Now, if you want to have any mixing, the first condition you see that you need to have these off-diagonal entries comparable to M2 or mu. Okay, so if you want to have any mixing, meaning if you want to have M1, M2, mu, M2, mu mixing, okay, then there should be these terms should be comparable to M1, M2 or mu. If you want to have here mixing, I mean, say for example, I say Vino mixing or Vino Hexeno mixing. Okay, so anything essentially. Okay, not Vino or Hexeno mixing or etc. Any of these things mixing, you need to have either M1, M2, mu or comparable to MZ essentially. This is an important condition that because these are the only off-diagonal entries which can play a role. Okay, these are the only off-diagonal entries which can induce some amount of mixing. So if these off-diagonal entries are sizable or comparable to M1 and M2, you will have some sort of a mixing essentially. Otherwise, you'll end up with having some pure states which are pure Vino, or a pure Hexeno. So again, you see the tension between SUSY breaking terms and standard model terms like MZ, essentially standard model contributions like MZ. Okay. Any questions on this?
So the hexenos are always mixed among themselves, right?
They're maximally mixed.
Yeah.
Okay, so this is 1 by root 2, 1 by root 2.
Yes.
This mixing is just 1 by root 2, 1 by root 2. So you can diagonalize it very easily.
And so in order to have a mixing, will this beta or tan beta also play a role, or it's only MZ?
No, see, say for example, cos beta goes as 1 by tan beta, roughly.
Yes.
Okay, so 1 by tan beta. So it plays a role, but not as significant as, say, for example, so other parameters are fixed. Okay, sin beta is order 1. So for example, if tan beta is greater than 5 or 6 or something, sin beta is already 1, order 1. So these terms are insignificant. These are order 1. So this is essentially mz sin theta W, mz cos theta W. Okay. Now cos beta goes for reasonable values of, so it just goes roughly as 1 by tan beta. For larger tan beta, say for example, sin beta, this is cos beta, right? Cos beta.
Cos beta.
Yeah. So for larger values of cos beta, okay, for larger values of tan beta, so this term will become even suppressed. So it becomes even harder to get larger mixing. Okay, especially with okay. So one component you can make it. So one component you can mix it reasonably okay. The other component becomes much harder with heavier and heavier larger and larger tan beta. Okay. So I think last time we discussed this, that so cos beta is root of 1 plus tan square beta. So this is nothing but 1 by tan beta. Okay, sin beta is cos beta tan beta.
Yes.
Okay, so this is 1 by tan beta times tan beta. So this is order 1. Okay.
Yeah.
So okay. So the only thing which can play a role is cos beta. Whenever there is a cos beta, it can play a role with respect to non beta. Okay. Okay. Now these are neutralinos. So this is important, and sometimes one should always be careful in supersymmetric theories because there is always this 1/√2 factors. The most dangerous ones are these 1/√2 factors and minus signs. So it is always good to keep some standard reference with you because it's very hard to derive everything from the beginning again and again for a given metric and everything. And of course, you can do it, but so with this, you want to derive the Feynman rules and so on. So, and because it's Marana case, so there will be the propagators would be different. So, and so on. So there are all these issues essentially. So it is always better to stick to some standard reference. Like for example, there is a couple of standard references. One is the soft supersymmetric Lagrangian. But I don't know all the other orders, but Steve King is there. Okay. And then there is also this new, the old one called Haber and Kane. This was a standard reference for all of us. And of course, you can use Martin's. Actually, Rohini's book is also good. Martin's primer. So these are good stuff actually to look at, and keep a book with you. Follow the reference carefully, and because all these things, whether you have a minus sign here or not, all these things can make a difference actually in your final spectrum. So you have to be consistent with your metric, with your epsilon alpha beta, and n number of things, and also your √2 factors essentially. So I suggest that you follow some, but I'm not saying book, but I'm not saying you should not know how you derive these things. You should know how you derive these things. At the same time, you should know, you should also have some standard reference so that you don't have to derive it again and again and again and again. Okay. Okay, Chargino mass matrix. So before going to Charginos, I'll just say one important point actually here about the neutralinos, because I already mentioned about the Bino mixing. So normally you do some diagonalization of the neutralino mass matrix. Like I said, in the limit, if M1, M2, mu are much greater than MZ, the diagonalization matrix is very simple. So what it will be? It will be just n is equal to 1, as Camille has just pointed out. It will be just 1/√2, 1/√2, 1/√2, 1/√2. Okay, this will be just the diagonalization matrix. But in general, if this condition is not true, okay, if this condition is not true, you have to generalize, you have to diagonalize it like Marana mass matrix. So because it's a Marana matrix, you should have some n star Mn n dagger is equal to some diagonalization matrix. And this diagonal entries would be, so these are called, these have standard M chi 10, M chi 20, M chi 30, M chi 40. So this is the neutralino mass matrix. Okay, so these are your neutralino eigenvalues. And this is the lightest neutrino. And this is the neutrino mixing matrix. No, unlike the standard, it is the same U. It's just, because it's a Marana mass matrix. Note that it is the same N sits on both left-hand side and right-hand side. Okay. Okay. So it's the same N which sits on the left-hand side and the right-hand side of the mass matrix. This is because, unlike the standard biunitary diagonalization, because this is a complex symmetric matrix, you have the condition. What is the, okay, just some linear algebra. Let me just, I know all of you know this, but I'm just saying it for completeness. So what is the standard theorem in linear algebra say? The standard theorem in linear algebra tells you that if you have a complex matrix, you can diagonalize it by two unitary matrices such that UU dagger is equal to 1 and VV dagger is equal to 1. Okay. So this is the standard theorem of linear algebra. This you can find in various places actually. And the old linear biunitary. Okay. Here M is complex, generic. Okay. It's complex generic means it is non-symmetric and everything. Okay. But if you put the condition that M transpose is equal to M, okay, from this only you get all these conditions that if M is Hermitian, what happens? If M is complex symmetrics, what happens? So you have condition. Now you can put the condition, what happens? You take the complete transform symmetry of this. So you take the transpose of this entire thing, take transpose, and equate the right-hand sides. So right-hand sides will remain the same thing. M diagonal is equal to M diagonal, transpose is equal to M diagonal. So when you do that, you end up having this condition. So you'll have N star Mn N dagger, because you'll have conditions like U is equal to U is equal to V star. Okay. So on. So these conditions will come. So the U and V will not be independent matrices, but they'll be related matrices. You can just check it yourself. Okay. So if you take, say, for example, the transpose of this will be V star M transpose U dagger, U transpose, sorry. Is equal to M diagonal. Okay. So this is the same, M transpose is equal to M. You can replace it with that. So you have the conditions that U is equal to V star and V dagger is equal to U transpose. So you have this condition. So it's no longer independent matrices. So there will be one unitary matrix, but only one unitary matrix, which comes on both left-hand side and right-hand side, essentially. Okay. So anyway, this is a simple thing. We'll use this again and again. That's the reason why I said it, because for all the matrices, we have to tag lines. Okay. Okay, good. Okay. So now we'll come to charge intersector. Here, the mass matrix is given. Transpose is equal to -1/2 W tilde H1 tilde M2 root 2 MW sine beta root 2 MW cos beta mu. This is W tilde plus H2 tilde plus. Now, this matrix is completely different compared to the ones which we have seen earlier, essentially. First of all, these are two different Weil fermions. This is a different Weil fermion. 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 And this matrix is not symmetric. Not symmetric. So this is a charge in a mass matrix. Now here again we see this comes from the soft terms. This comes from the mu term. Okay, and the superpotential. This comes from a combination of getting a web. Okay, only for the W bosons, essentially, only for the W bosons. Okay, this comes from W2, okay, this is a neutral Higgsino, neutral Higgs, W minus H2 plus, and so on. So, and this one would be H1 minus W plus neutral Higgs. So this is coming also from the Kähler potential. Again, the terms like what do you call the terms like which look like Yukawa couplings, but which mix the Higgs-Higgsinos and Gauginos. Now notice that it is proportional to MW. Why it's proportional to MW? Because there is no G square. It's only proportional to G square. There is no G prime square. It's only proportional to G square. So that's the reason why you have only MW. Because this mixing of the charged neutral happens only in the SU2 case, not the U1 case. Because in the U1 case, there is no charged one. So there are no charged particles. Okay. So the mixing between charge and neutral happens only for the SU2 case, not for the U1 case. Now this is diagonalized by this. So diagonalization is done by, so U star MC P dagger is equal to diag M chi1 plus M chi2 plus. So this is from a biunitary transformations. Okay. So this is these are the two chi1 plus and chi2 plus, which are mixtures of the two charginos. They contain chi1 plus minus, and which is a mixture of both Vino and Higgsino. Again, if you limit M2, in the limit M2 and mu much greater than MW, what happens? This is just diagonal. You have pure Vino and a pure Higgsino. Pure Vino charged and a pure Higgsino. Okay, this is not relevant for us, but for dark matter, it's not relevant for dark matter, but this is what happens actually. Charged, okay, pure Higgsino charged. But the limit, and the limit when this starts mixing, okay, they start mixing. So when M2 mu becomes closer to MW, so the most general mass matrix should be diagonalized by using a biunitary transformation. Now, if you have biunitary transformations, how will you find out U and V? U and UV will give me by MC dagger will give you U. Okay. This is because this is diagonalized by U. Okay. M chargino square diag square of the M chargino mass the eigenvalues, and whereas the opposite combination MC dagger MC is diagonalized by again diag M chargino square square anywhere you can put anyway, okay, because it's the same thing because it's a diagonal matrix. So this gives you U, and you can determine V by taking the combinations MC MC dagger and MC dagger MC. That way you can determine each of these chargino mass matrix, and these are Dirac particles. These are not Marana. So these are Dirac particles. So they have they have the standard what do you call Feynman rules and everything like for Dirac particles. Okay. Any questions on this? Okay. Okay. Let's continue. So this is about the chargino mass matrix, and then we now go to the S fermion sector. So this fermion sector means essentially stops, squawks, all the squads actually. So all the squawks, leptons. So in squats, there are two of this. Here also there are two. Up type, down type. Here also there are two, which are essentially neutrinos, neutrinos, leptons. Okay, so we had to, in principle, see 4 lepton mass matrices. Okay, so what does electroweak symmetry breaking do for these things? So, so let's remember the lepton mass matrices. So I'll try to make some simplifications so as to make our life easier. So the first thing is we write down soft terms. L soft contains M, okay, EL tilde, say for example, Q, okay, we'll start with Q. So Q I tilde square, QI tilde dagger, QJ tilde. So this is nothing but M UL tilde square, UI tilde the star ULI plus DLI tilde square, DLI J DL tilde star. So both of them have the same mass, which is essentially MQ tilde square. Essentially, all the left-handed particles in the same multiplet have the same masses, MQIJ. Now, if you remember correctly, I said I not equal to J is also allowed. So that means this is a 3 by 3 matrix. Each of them is a 3 by 3 matrix in flavor space. So this is the first contribution in the soft terms. Okay. So this one will not have any generic thing. Okay. So the next one is F terms. So F terms give you, because they give you del W by del phi I square. Okay. Remember the superpotential. Okay, let's look at the superpotential in the broken space. The superpotential is nothing but HU IJ. Did we use HU or YU? I don't remember. You just see H2. Maybe let's use YU, because YU IJ. Okay, YD IJ QI DJC H1 plus YE IJ Li EJC H1 plus mu H1 H2. Now each term contains all possible Yukawas. It also contains the Higgs getting a vacuum expectation value. So YU IJ times UI UJC, this is here, and H2. Okay, these two are fermions, and this one is a Higgs neutral. The Higgs neutral, which is nothing but your phi. This expansion we have seen in great detail in both in supersymmetric QED as well as in MSSM. So it also contains terms of this type. So this gives you, once this gets a vacuum expectation value, this essentially becomes YU IJ VU by root 2 UI UJC. This is nothing but your mass term. This is nothing but MUI square MUI UI UJC. Okay, so the superpotential also has mass terms. In other words, now if you take F term, del W by del QI, this also will contain UI UJC. No, it should not. You will call it as F term, but essentially it's not completely scalar. Essentially, it's not completely. So the corresponding. So F term, the corresponding term, F term is completely scalar, right? So QI. This will give me completely scalars UI tilde, UJ tilde C, and phi H20. This is also completely scalar. Okay. Oh, sorry. This is not good. So QI would be so UI tilde MUI star. So if you take a square, mod square, it will give me, okay, this is F square, will give me, if I take a square of this one, UI tilde star UI tilde MUI square. So this term comes from this term essentially. Okay. So MUI, so if you diagonalize Yukawa couplings, just imagine that I diagonalize Yukawa couplings, I set it to one diagonal terms. So this gives me UI square. So this is not UI USC. Remember, this is not UI USC. Such term also will come from F term, that will come to it in a second. Okay. And so this gives me a mass term only for the left-handed particles, only for the left-handed particles. So there is a term also coming from the F term. And then there is also a D term. I'll give you the general formula so that you don't have to worry about it. The D term would be G square plus G prime square. So all possible terms. Then you will tilde square, so on. So all the formal possible terms. And then you have, at the end of the day, H2 square minus H1 square, whole square. So what happens when you expand the square, you'll have one term corresponding to UL tilde H2 square, okay, expanding the square. You'll have terms proportional to V square, okay. You'll end up having terms which are proportional. You'll end up having D term contributions for UL tilde square, okay. D term contributions. I'll write down the general formula for this. Essentially, just you can re-express it in terms of the mz square, essentially term contributions. So this is only for the left-handed part. This is only for the left-handed part. Now, similar things you can write down for the right-handed part also. But the fun comes, so F terms, soft, left, they're symmetric, sort of, right? In the right-handed part, the D terms will not contain G prime square, will not contain G square, they will only contain G prime square, because right-handed will not contain G square, because right-handed doesn't participate in SU2 interactions. So you'll only have G square, G prime square. So then what about left-right mixing? The left-right mixing comes from two terms. And one is the A term, A, which has the same form as a Yukawa coupling. A terms which you don't know, all scalars. So when H2 gets a wave, this gives me AT U tilde U R or U C tilde, sorry. V2. So this is one particular combination you'll get. There is also another left-right mixing comes from the F term. If you take, so for example, in the superpotential, you have Q U H2 minus mu H2 H1. So Y, say for example, let's just take one simple Yukawa coupling. Now if you take a H2, okay, this is your W. Now del W by del H2, you'll get a term YT Q U mu H1. Okay, so this will be YT mu Q U H1. And so this is a mixing with the wrong type of Higgs, All of them are scalars, remember, all of them are scalar. So you have up-type quarks mixing with the wrong type of Higgs, essentially. Wrong type of Higgs means they're not mixing with up-type Higgs, but they're mixing with down-type Higgs. So this kind of terms are possible. So up-type, down-type, and wrong type. So that's the reason why, okay, or wrong Higgs. So when the Higgs get a waxing expectation value, this gives me some V sine beta or cos beta sitting here, essentially. Okay. So you have left-right mixing, This is left terms. So the most general formulas I'll write down now. Are you all convinced with this? Are you all convinced with this? Okay. Hello? Meaning, okay. I'm hoping you're convinced. So the most general formula Mij square is equal to any mass matrix del square del phi I del phi j star del square V del phi I del phi j del square V del phi j phi star del phi j star del square V. This is the same formula in all scalar theories. Okay, del phi I star del phi j star phi j. So this is the general formula. You take the scalar potential, take the derivatives with respect to phi I, phi j star, phi I, and write down the most general formula. So in supersymmetric case, M soft terms, lepton mass matrix, is given by M left-handed, M left-right mixing, M left-right mixing dagger, M right-handed. Okay, you can write it into. So in general, these are 6x6 matrices. Okay, these are 6x6 matrices because each of them is a 3x3 matrix. This is a 3x3 matrix. This is a 3x3. So these are in general 6x6 matrices. I'll tell you when it comes down to normal thing. So you have MFL Li Lj square is equal to M square, the soft term, Li square, okay. Left-handed Lj square, left-handed, plus Mf square, the corresponding fermion mass, times delta Ij, plus Mz square cos 2 beta times T3 plus sine square theta W QEM, the charge of this particle, times this also is contained. Okay, I can just write this entire thing. Whole into delta Ij. So you see, okay, now let's just repeat. This one is a 3x3 matrix in which I not equal to J is possible in the soft terms because this can violate flavor. Whereas the F terms and the D terms, this is your D term, this has a formula like this. This is the T3 value and the charge Y value or Y or electric charge value. Mz square cos 2 beta, and this is nothing but G square plus G, D term essentially, G square plus G prime square, okay? So this is nothing but Mz square cos 2 beta comes just from this one. The D term, okay, I'll write it down somewhere here. Okay, here. So this is nothing but, so this gives you terms which are roughly G square plus G prime square. Now, if you take V square outside, this gives me cos square beta minus sine square beta. So this is nothing but Mz square cos 2 beta times some formula essentially. Okay, this is essentially what it is. Okay, so, but this is all diagonal. Okay, note that this is delta Ij. So in the flavor space, This is diagonal. Okay. And then mf square tilde LR RJ tilde is equal to Y F. Now this changes for the up type and down type. This changes for up type and down type. So this is nothing but a term. Okay. This is nothing but AF, YF, a term, if I just write it down. Now for the down up type, this is comes as V1 minus MF mu cot beta. For uptype. Uptype means stops, uptype squawks essentially. There only one uptype, squawks, or in the electronic sector, you don't have this left-right mixing because there are no right-handed right-handed neutrinos. Okay, if there are right-handed neutrinos, this term will make a difference for neutrinos. But since there is only uptype squawks, this is it. For the neutrino mass matrix, there is no left-right mixing. So there is no left-right mixing for the neutrino mass matrix because there are no right-handed neutrinos, so there are no right-handed neutrinos. Okay, now this will become YF AF V2 minus MF mu tan beta for down type quarks, squarks, and charged leptons. So you keep hearing there's a large enhancement in the large tan beta limit. There is an enhancement of enhancement of the left-right mixing in the down type squawk. So this is a term. This is a term which leads you to enhancement of the left-right mixing in the down type quarks essentially. Okay, in the large tan beta limit. And then there is a right case. The MF R square IJ plus MF square plus MZ square cos 2 beta. Same thing. Sine square theta W. There is no TT EM times delta H. There is no T3 because right-handed neutrinos, they don't really have T3. Right-handed particles don't have T3, so there is no T3 value. Okay, so together, now this looks like a formidable thing, 6x6 matrix. So in general, you have to diagonalize by some UF MF square, which is the full. So this will be 6x6 MF square diagonal. So this will be 6x6 matrices. So you have to do a 6x6 diagonalization in principle. But for most cases, what we do is for most of the time, to reduce the number of parameters, and to take into consideration flavor constraints. What we set is these terms, the soft terms, these soft terms also, all these soft terms also will set it proportional to delta ij. Okay, so we set mlij tilde square is equal to ml square ij delta ij. mrij tilde square is equal to mrij delta ij. Okay. So we set, essentially what we are doing by this is setting all the flavor violating terms to 0. So you just set all the flavor violating terms to 0. Okay, that's a very good assumption. And in fact, when we see supersymmetry breaking models, most of the models, popular models, because that's how you construct them, will lead to this condition that all the soft violating terms are 0 essentially. Okay, flavor violating terms, soft terms are set to 0, are 0. Okay, so in that case, this entire 6x6 matrix decomposes into 3 times 2x2 matrices. Further, what happens is that because these are 2x2 matrices, so let's just see what these are essentially. Let's take example. I'll do an example. Uptype quark. So uptype quark matrix. Okay, so let's do this uptype quark mass matrix. So this mu tilde square will be a 2x2 matrix. So this will be mu tilde square plus mu square plus d term. Okay, I'll just write it as d. And this mur tilde square, mu square plus d, this is dl, this is dr, d term. Further, what happens is, for the first 2 generations, this off-diagonal entry is also proportional to mu. Okay, mu times, this is at minus mu cot beta. This will be au times mu cot beta, au minus mu cot beta. Maybe it's a plus sign, I think. There is a relative sign. Okay, maybe there is a plus sign. Okay. So what is happening? This term is also very, very small because it is suppressed by the echo coupling of the uptype quark. You know that the first 2 generation masses are very, very small. Okay, there are 6 orders of magnitude smaller than a top quark or any of the other things. So they will be smaller than any of the soft terms here. So if you look at this mass matrix, all these other terms are completely irrelevant except these ones, okay, which can be comparable to the diagonal ones. Only when this can be comparable to the diagonal ones, then it makes sense. Otherwise, all the other terms can be just be neglected. For the first 2 generations, you see that even if you want to take them to be comparable, so even if you take at, mu, all of them equivalent to m sub z, say for example, even if mul tilde, mur tilde, at, all of them are same, say roughly equal to mu, or are same to some scale m sub z. Okay, even in that case, so you'll have mu square. This is m sub z square. This is mu times m sub z This is mu times m SUSY square. Even in that case, this is extremely small, extremely small. This is extremely small, so you set it to 0. Essentially, you can neglect it. Even if you don't set it to 0, it doesn't matter. So you consider for first 2 generations, left-right mixing can be safely neglected. Okay, so the first 2 generations you can completely neglect left-right mixing. So the left-right mixing only plays a role for the 3rd generation. So the 3rd generation, essentially, say for the stops, which plays a very important role. So we will consider the stop mass matrix. This is important. Okay, MTL tilde square plus MT square plus DL, MTR tilde square plus MT square plus dr, because MT is not a small quantity. Here you have YT times AT plus mu cot beta. YT times AT plus mu cot beta. So this term is also called sometimes XT. Okay, the left-right mixing part. This we will see once we come to the Higgs. Maybe today or maybe in the next class we'll do the Higgs. Okay, so this plays a very important role in the Higgs phenomenology and Higgs in the Higgs computation essentially. So this is nothing but YT times XT. Okay. Then the other ones is M bottom square. Okay. Here YT is order 1. Remember that YT is always order 1. It's a very large quantity. The bottom mass MBL tilde square plus MB square, bottom mass square, D right, YB, AB minus mu tan beta. Oh, maybe this is minus sign. Sorry, I think I should have done AT plus mu cot beta. You have to be careful this plus signs and minus sign. Okay, and BR, I'll just check it. Oh, okay, just check the signs. Okay, I think they are the same. I think they may be the minus sign may be the same. Okay, it may be just 80 plus mu cot beta. I think if I remember correctly. This is minus sign. I think what I wrote earlier is correct. I think, but let me just. I'll check it in the next class. BR tilde square plus MB square plus DR, the term R. And for the tau, you have M tau square, so M tau square plus 0, Y tau, A tau minus mu tan beta, M tau R square plus M tau square plus DR. Okay, so this is how. Now, if you diagonalize this, these are 2 by 2 matrices. So first 2 generations don't require any diagonalization, whereas the 3rd generations requires diagonalization because 3rd generation could be lighter in principle. We'll come to that when we study the spectrum a little bit. Could be lighter in principle, maybe closer to the standard model masses, especially closer to the stop mass. So let's just do the diagonalization for the stop mass matrix. The stop mass matrix, you can diagonalize it by one angle, just by one angle. Okay, so this is like you can have cos theta t sin theta t or minus sin theta t cos theta t. Then stop mass matrix squared, then cos theta t sin theta t cos theta t is equal to diag m stop 1 stop 2. These are your two stop mass matrices. I'm focusing only on the stops because this is important for my Higgs discussion. So this diagram. Now, how is this theta defined? Tan 2 theta t is equal to 2 yt xt divided by these two terms, divided by essentially m stop r square minus m stop l square. Then there is also dr minus dl, and the top mass just cancels off essentially. Okay, you can forget about the dr dl. So roughly it's the difference between the two stops, left and right stop masses, and the off diagonal entry essentially. This is tan to 30. How is it defined? Okay, so this stop mass matrix plays a very, very important role. Now, okay, so when you are discussing S-fermion mass matrices, there is one important condition you have to put into consideration. Okay, very, very important condition. Okay, that is essentially none of the soft terms, none of the S matrix soft terms, because they're dominantly okay. So most of the S-fermions masses are dominated by their soft masses. So except, say for example, except for the stop, okay, you can forget about bottom and stove also. So even if I neglect stove and bottom, in low tan beta limit, stove and bottom will not have large mixing, okay? But in the large tangent beta limit, stove and bottom can have large mixing. If you take tan beta is equal to 50 or something, so they can have reasonably large mixing between left and right. Okay, so independent of that, okay, just for a second, let's just look at that most of the S-fermions are dominated by soft mass. Now, the main condition is that these soft masses should not become negative, because the moment they become negative, okay, none of the soft masses can become negative, especially for these particles. Okay, because all these particles are either containing charge, except for neutrinos. Neutrinos is a different thing, except for neutrinos. Okay, because they are neutral. All these particles contain color charge. They are scalars. These are scalars. They have color, charge, and SU2 quantum numbers. So forget about SU2, okay? So they have color and charge quantum numbers. So they should not attain vacuum expectation values. So this puts the condition that all eigenvalues of the soft term, soft masses, matrices should be greater than 0. So that means they should not, the determinant should always be positive. All the soft terms, meaning they're dominated by, okay. So all the soft mass matrices should not get a wave. So that means none of their eigenvalues should become negative, because if they get negative, you can generate a vacuum expectation value. They can generate a vacuum expectation value essentially. This condition, okay, is easy for first two generations, because the first two generations don't have left-right mixing. In the presence of A terms, this condition becomes slightly complicated. You can write an analytical condition. You should not have any field direction in which, in the presence of left-right mixing, LR mixing. So that means for third generation, this condition becomes slightly complicated. We don't have to go into the details, but this condition should make sure that the lightest eigenvalue, the eigenvalues are always positive. So in a way, say for example, if it is top mass matrix is essentially TL square, TR square, and YTXT, or MTXT, say for example. So it means that there should not be anything MTR squared. If the lowest eigenvalue is something like this, MTXT should always become positive. So some conditions very similar to this should be valid, so that the stops do not get a wave vacuum expectation value. Okay, if there is no mixing, this term will not be there. This negative term will not be there. If there is a mixing, this negative term also will appear. But the actual condition is slightly complicated. You can look at Casas and Dimopoulos, old 93 paper. But these are called charge and color breaking minima conditions. Okay, these are called charge and color breaking minima. So this is a very, very important condition on the stop mass matrix or any of the fermion mass matrix, that they should always be positive. Okay, I can go into the details, but this is not sufficient. This is sufficient for us for the present. If you need more details, we can go for it. Okay.
So one thing.
Yeah.
So here, if this mass eigenvalues are negative, so they can attain a wave. But if the wave is such that, I mean, still our Higgs potential, I mean, that is the minimum. So is that still okay? Or, I mean, they should never attain any wave?
No. Okay. Okay. So the point is that, like, suppose the moment so because it's a combination of different scalar fields now. You have the Higgs fields and the stock fields. Okay. Suppose if the stock field gets a wave, but its wave is very short-lived. In a way, that means that it is very shallow wave, and the wave of the Higgs is much deeper, say for example, okay, in which there is no color and charge breaking minima. Okay, and it's much deeper, and so this wave, so even if the universe falls into this wave, okay, it is not a metastable or stable wave. That means it's not the global minima of the entire potential. And so but it is very short-lived. So the universe will just immediately decay and goes back to the deeper wave. Then it's possible. Okay, you should not have metastable minima, which are metastable means minima in which the lifetime of the universe is longer than the age of the universe, or comparable to the age of the universe, or longer than the age of the universe, but it's not the global minima. Okay, there could be global minima, but the transition time between this minima and the other minima is very, very long, such that by the time the universe decays into the other minima, the transition happens to the other minima, the age of the universe is already gone, essentially, meaning it takes more than the age of the universe, and so on. So, okay, but that should not happen. It should not be a metastable minima. It should not be a stable minima.
Okay.
Okay.
Yes.
Otherwise, you are breaking color and charge.
Okay. Mm-hmm.
Okay. As long as these two conditions you maintain, sure that it is not it's not stable or metastable, but it could be some short-lived minima. The transitions would be very fast. Then you are fine, I think.
Okay.
Yeah. These actually lead to the conditions that A terms. Okay, I'm writing that. Okay, so this leads to these conditions. The Casas de Mopol conditions tell you that A should be always be less than 3 times m sub 0, roughly. This is roughly. As long as this condition is satisfied, you will never fall into a vacuum expectation value in which the universe has a charge and color breaking minima, which is either metastable or stable. This can be refined further. This depends upon how many fields you are taking when you are doing the minimization. See, minimization of multiple scalar fields is a very complicated case. Numerically, you have to do it. You have to actually construct it numerically, and we have done for 3 field and 4 field. It's extremely complicated. Okay, and you had to compute. But now things have become easier because there are some analytical solutions compared to what we did earlier. Now there are some analytical solutions for the action, the transition amplitude between the deeper minima to the, it's also called the bounce action, or the Coleman-DeLuca and DeLucia bounce action. There are some analytical solutions for these things, and so one can actually calculate these lifetimes much better compared to the earlier. One has to use something called Cosmo transitions, and it took a long time. But these days, I think you can do it in much better. But I don't know if anybody has done it for supersymmetry in the recent times. This happens for any more than one field. Okay, if you have 2 Higgs doublet model, also you can ask this question. Okay, to Higgs doublet model, the charge Higgs should not get away. Okay, that could lead to some conditions actually. I don't know if it has been studied in great detail, like with using all these bonds, actions and everything. But that's something one can look at. One should look at. Okay, and so similarly, 2 Higgs doublet models, or a generic 2 Higgs doublet models, or any models with 2 Higgses or more than 2 Higgses. People are looking at 3 Higgs doublet models also. So all this, anything with more than one scalar is complicated. SUSY has several scalars. So the minima is super complicated. Of course, then you make assumptions saying that, okay, only the third generation is important, only the stop fields are important. You forget about bottoms and stops and stows and everything, especially in the last tangent beta region. Okay. And then only focus on stops. and the 2 Higgses. So you can derive, you can do the computation. Okay. Otherwise, the generic problem is super complicated. Okay. You set essentially D terms to 0, you go into the D term directions in which the D terms are 0. And so you can have a good analytical handling, but a full computation is complicated, meaning full numerical solution and full precise boundaries are, meaning in the parameter space is slightly complicated. You can get a good estimate with analytical conditions like this ones, like AT should be less than 3 times M sub Z. Those kind of things you can get. Okay. But yeah, but these things should be relooked at with this new technology. I don't know. One should look at it. These things become important because the Higgs mass is measured well and the lambda is known. So this is true even in standard model, but one can also look at, people have looked at in effective field theories, but I'm not sure with in 2 Higgs doublet model, they have looked at it in terms of RG equations, but a full analysis like with the bounce action and everything has not been looked at as far as I know. Actually, yeah. I may be wrong, but okay. Any further questions? Okay. Now we had to do the Higgs sector. I thought I'll finish Higgs sector today, but it's already 1 o'clock, 1:10 or something. So maybe we'll do it on Thursday. We will do it offline. Is that okay? Thursday?
Yes.
Okay. Okay. Then we'll do it offline on Thursday. Okay. And that,
Yes.
yeah, that brings the interesting part of MSSM, because the Higgs is the most interesting thing about MSSM. Okay. It leads to all kinds of consequences and everything. So any further questions on today's lectures? Okay. Okay. If you remember something, just send me an email or put it on Teams. Okay. All right. Okay. I'll stop now.
So this trilinear.
Yeah,
Hello.
I cannot hear you. I cannot hear you. Yeah.
Yeah. Yes. So this trilinear couplings, they can
Yeah.
also, I mean, they will also have this IJK, I mean, IJ indices, right?
Right.
So while making the assumption, we have also taken them to be, I
Yes.
mean, only same
Yeah.
flavor.
Exactly.
Okay.
Because the assumption for the trilinear, I didn't go into details, is that they should be proportional to Yukawa couplings. So it's slightly different compared to this one. So AU IJK should be equivalent to YU IJK times AU IJK. So this AU IJK is also proportional to YU IJK. So it has the same structure such that when you diagonalize YU IJK, so in the standard model, you diagonalize it. It also diagonalizes the same matrix, also diagonalizes YU IJK. AU diagonal. It's the same thing. Okay. So the same U which diagonalizes YU also diagonalizes AU. Okay. So that's the condition one imposes. So in the limit YU goes to diagonal, okay, it always means that AU also goes to diagonal, but this need not be true. But maybe in a couple of classes down the line, I'll discuss about before discussing one more class, maybe next Tuesday. Next Tuesday, I'll start discussing supersymmetry breaking models. Before doing that, I'll discuss a little bit about flavor constraints. And what you will see is that the flavor constraints on this left-right terms, like A terms, are very, very strong compared to the diagonal ones. Okay, so this is a very, very reasonable assumption to make. This is a very, very reasonable assumption to make, because the flavor constraints on AU, if it breaks away from the YU form, they're extremely dangerous. Okay, so they have very strong constraints. Okay. So it's a very natural assumption to make them to be almost having the same. They're aligned to YU. They're aligned to YU. So that means the same matrix which diagonalizes YU also diagonalizes AU. Okay. Yeah. So this is slight distinction in the left terms and the right terms. You assume them to be diagonal. In the YU case, A terms, trilinear terms, you assume them to be proportional to YU. Okay. Yeah.
Okay. Thank you, sir.
Yeah. I'll discuss the flavor violation in each of these cases. I won't go, but at least I'll give you a flavor. I may not go into the full details, but I'll give you a flavor before going into a supersymmetric. Yeah. Anyway, okay. If you remember any questions or something, just drop an email or put it on Teams or something. Okay. Yeah. Okay. Any further questions? Okay. Okay, let me stop here.